Hi everyone. In this module, I am going to explain chemical spectroscopy. This is the syllabus of Karnataka State Open University, MSc, second semester, paper Chemical Spectroscopy, Block 1, Unit 2. In that Unit 1, we discussed the fundamentals of spectroscopy. In that Unit 2, I am going to explain the concept of relationship between energy and matter, electromagnetic spectra, radio frequency wave, infrared region, X-ray region, energy level of atom, electromagnetic radiations with atom, and energy level diagram for a molecule. Finally, molecular energy levels and associated spectra. Generally, the radiation is the energy that travels through a media. We consider that the visible light that comes from the lamp in our house. Consider the radio waves from radio stations, make microwaves used for cooking in kitchen, IR and UV light used in industries and laboratories for various purposes. Consider other rays like that X-rays used in medical field or some of the examples of these radiations which we are used in our daily life. All these radiations are the type of electromagnetic radiations. Simply that is called what? EM radiation. Each type of radiations have particular property and have definite characters, means they have a different wavelength and different frequencies. Consider that radio captures radio waves emitted by radio stations, bringing our favorite fuels. Radio waves are also emitted by stars and gas in space. The microwave radiations will cook and also used for astronomers to learn about the structures of nearby galaxies. The infrared radiations, night vision goggles pick up the infrared light emitted by our skin and object with heat. In visible radiation, detect the fireflies, light bulbs, stars all emit visible light. The ultraviolet radiation is emitted by the sun and is the reason skin trans and burns. A dentist uses X-rays to image our teeth. The reasons the airport security uses them to see through our bag. Hot gases in the universe also emit X-rays. Finally, gamma rays. Doctors use gamma rays imaging to see inside our body. The biggest gamma ray generator of all is the universe. These different types of radiations generally they called what? Electromagnetic spectra. Electromagnetic waves exist with an enormous range of frequencies. This continuous range of frequencies is known as the electromagnetic spectrum. The entire range of the spectrum is divided into specific regions. This subdividing of the entire spectrum into smaller spectra is done on the basis of how each regions of electromagnetic waves interact with matter. Just we consider a figure 1, it is the overview of the entire electromagnetic spectrum. These electromagnetic spectrums dividing into 6 major sub-regions in increasing order of frequency. The regions are named as follows, like that: radio frequency region, microwave region, infrared region, visible and ultraviolet region, X-rays region, gamma ray region. Now I am going to discuss with Bohr's atom energy level of atom. According to Bohr's atomic model, electrons travel around the nucleus in specific permitted circular orbits. Each orbit is at the fixed distance from the nucleus and has definite energy. As long as for electron circulating in these orbits, they do not emit radiations, they did not lose or gain energy. All the electrons try to occupy the orbit which is lowest in energy and electron resides in this are called ground state. The energy difference between the two orbits is equal to delta E is equal to R into 1 by N1 square minus 1 by N2 square, where R is Rydberg constant value. Its value is equal to 109678 per centimeter, and N1 and N2 are the two different orbitals, where N1 is lower energy orbitals, N2 is higher energy orbital. Here, once these electrons in atom at ordinary temperature resides in the lower energy state, that is ground state, electromagnetic radiation corresponds to energy of delta E. In the equation 2 is absorbed. Here, once this transition connecting, here electron jump from higher energy level to lower energy level, N1 is equal to 1. That is called what? Lyman series. Electron jump from higher energy level 2, 3, 4 up to infinity to lower energy level, N1 is equal to 2. That is called what? Balmer series, following Paschen series, Rocket series, and P-Fund series. The interactions of electromagnetic radiation with an atom. Anyhow, in this unit we have to discuss the spectroscopic constant. All electromagnetic radiation strike an atom. It can cause a number of changes. An electron residing in lower energy molecular is promoted to higher energy orbital. The change in energy level is called a transition. Such a transition happens only when the energy h nu of the electromagnetic radiation is exactly the same as the energy difference between the two orbital energies. That is called what here? Electronic transition. And the absorption process is called what? Electronic absorption. Those electrons will remain in the excited state for the certain period of time and then will return to lower energy state while remitting energy in the exactly amount of the difference between the two energy levels is called emission process. Here we consider that NMR it is observed in this region. This is the wave number, corresponding wave number. These are all the NMR, ESR, microwaves, infrared waves, UV visible light, X-rays, gamma rays are observed in this region. This is the overview of intermolecular interactions of molecule with different electromagnetic spectrum. Next, energy level diagram for molecule. Molecules are formed by uniting two or more atoms. The formation of bond between the atoms in a molecule is due to overlapping of atomic orbital. According to that molecular quantum mechanics, since nuclei are much heavier than the electron, nuclei are treated as stationary so that electrons move relative to them. We consider that overall energy is calculated by using the formula E is equal to E electrostatic electronic plus E vibrational plus E rotational. Next, molecular energy levels of associated spectra. We consider that diatomic molecules is a stable arrangement of two atoms separated by a distance called bond length. If the molecule is formed by two same atoms, then the molecule is said to be homonuclear molecule like H2O2, F2Cl2, etc. If the molecule is formed by two or more different atoms, then molecule is said to be heteromolecule. The energy level of molecule is different from that of individual atoms. Like atomic energy state, we cannot classify molecular energy state according to the electronic angular momentum. When this molecule absorbs, the energy increases, which is equal to by absorbing appropriate quantity of energy, which is exactly equal to the energy difference between two levels. Here just we consider this. The internal energy is equal to the sum of the electronic, vibrational and rotational energy. The molecular spectra are divided into three spectral range, corresponds to the different types of transition between molecular energy states. They are electronic spectra, vibrational rotational spectra, and pure rotational spectra. Next, just we conclude this unit. For many years, the scientists have exploited the way that radiation interacts with matter, the particular effect that matter has upon light depend on the energy, content of the radiation and type of matter. In all causes, scientists measures the wavelength, radiations, it undergoes changes that may or may not be reversible, that depend on the energy of radiation. For example, gamma radiation can cause matter to lose electrons and undergo irreversible changes. Just to go through this, these are all the important questions regarding this topic. Next, Unit 3. From this Unit 3, we have to discuss the introductions of electron spin resonance, basic principles of electronic spectroscopy, electroscopic splitting factor, relaxation, that is spin relaxation mechanism, spin lattice relaxation, spin relaxation, width and position of the spectral line, hyperfine coupling constant, isotropic and anisotropic interaction, and super hyperfine splitting, etc. In this unit, the introductions like that, the electron spin resonance spectroscopy is relevant to the study of atoms, ions, free radicals and molecules possessing an odd number of electrons or unpaired electrons. In that, ESR spectroscopy is also called the electron magnetic resonance. Paramagnetic resonance, that is called what, EPR spectroscopy, and was first observed in 1945 by Zelensky at Ksou. The ESR spectrum is observed only for the systems containing unpaired electron. Thus, the system which can investigate by ESR spectroscopy are organic or inorganic free radicals and ions of transition metals which contains unpaired d or f electrons. What are that substances they act as and what ESR actually? So all configurations with an odd number of electrons must possess angular momentum and therefore must be paramagnetic in nature, that can be detected by ESR spectroscopy. The molecules such as NO and NO2 have odd number of electrons, therefore they are what, paramagnetic. The molecules such as oxygen, through having an even number of electrons, have a partially filled molecular shells and therefore paramagnetic in nature and can be detected by ESR. The atoms or ions with incomplete, means 3D, 4D, 5D, 4F, 5F shell. However, not all the valence state of the transition metal ions are paramagnetic. We consider that vanadium plus, these are all what, transition elements, simply that is called what, d block elements. Donors and acceptors such as phosphorus donor impurities in silicon, organic and inorganic radicals or ESR active. The activator and co-activators in phosphorus such as self-activated ZNS and conductions electrons. What is the basic principle of this ESR spectroscopy? The energy differences studied in ESR spectroscopy are due to the interactions of unpaired electron in the sample with an external magnetic field produced by EPR spectrometer. This effect is called the Zeeman effect. Just we derive that here electron possesses spin S whose values is of the magnetic momentum associated with this spin is given by mu is equal to minus ZGE HB mu B S. The energy associated with the electron spin S in the applied magnetic field in the directions of z-axis is E is equal to mu B Z. This is the way to calculations of this what? Energy difference between two spin states. Here H is Planck's constant, mu is microwave frequency, G is probability proportionality factor, which is a function of electrons environment, and it is called as Zeeman splitting factor. The spectroscopic splitting. From the relations of equations, there are two important factors to note. Two spin states have the same energy when there is no applied magnetic field. The applications of magnetic field provides a magnetic potential energy which split the electronic spin state and the energy difference between the two states increases linearly with increasing magnetic field strength. These are all what here we are going to calculate for that what ESR values. This is the ESR absorption spectra of an electron. Absorption spectra and first derivative of absorption spectra. That the spin relaxation mechanism. Here spin lattice relaxation, spin relaxation are there. In spin lattice relaxation implies interaction between the spin system and the lattice that is surrounding a molecule. Vibrational, rotational or translational energy are dissipated within the lattice. Next we consider that width of the spectral line. When both spin and spin lattice relaxation contribute to EPR signal, the resonance line width can be written as delta B is equal to 1 by TE 1 by T. ESR absorption position. That is what G factor. The different ESR spectrometers or operate at a different magnetic field. Hence it is desirable to express ESR spectroscopy gives that another way. What is that is G? G is equal to H mu by mu B. This is the formula we are going to calculate that. Consider example of this 1,1 diphenyl 2 paralhydride hydrazine free radical. This is mainly in the free radical state and its G value is 2.0036. Next we consider some other examples regarding to that. Calculate ESR frequency of unpaired electrons in a magnetic field of 3000 G. Here we know that formula delta E is equal to H mu. H mu is nothing but G mu B V naught. For free electron, G, H and beta values are substituted here. What we are getting? Values of G. The multiplied structures in ESR spectroscopy, there are two types of multiplied structures in ESR spectroscopy. They are fine and hyperfine splitting. In that fine structures, it occurs only in crystals containing more than one unpaired electronic spins. Suppose the crystal which contains molecules or ions with two parallel rather than unpaired electron spins. In this case, there would be a total spin 1, S is equal to 1 and 2S plus 1 is equal to 3. In general, there are n number of parallel electron spins present in a molecule. There will be n equally spaced resonance lines in the ESR spectrum. The spin-spin splitting. Hyperfine structure is resulting from the coupling of unpaired electron spin with neighboring nuclear spins. Next we consider that spin-spin splitting, that is also called what? Hyperfine splitting and hyperfine spectrum. This is what equivalent nuclei, this is what relative intensity. This is the hyperfine splitting in electron in nitrogen atoms, the influence of applied magnetic field. These are all the spectra. Next we consider the similar, the methyl radical. There are 3 hydrogen atoms are present. Therefore, each of the 2 energy levels of the single unpaired electrons on the carbon atom is coupled with nuclear spin of 3 hydrogen atoms. The number of peaks in ESR signals of methyl radical is split into 4 energy levels according to the formula here 2Ni plus 1. These are all different molecules. We are going to take in benzene, free radical. This is pyrazine, free radical. And hyperfine coupling constant. The hyperfine coupling constant is directly related to the distance between peaks in a spectrum, and its magnitude indicates the extent of delocalization of the unpaired electrons over the molecule. This constant is calculated using the following equations. The total energy related to the electron transition in EPR. These are all splitting between energy levels and their dependence on magnetic field strength. Like the isotropic and anisotropic interactions. Iso means same, aniso means different. Electron nuclei interactions have several mechanisms. The most prevalent being Fermi constant interactions and dipole interaction. The dipole interactions occurs between the magnetic moments of the nucleus and electron as an atom. Moves around the nucleus. Let's go through that. The Fermi constant interaction predominate with isotropic interactions, meaning sample orientations to the magnetic field does not affect the interaction. The dipole interactions predominate with anisotropic interactions, meaning sample orientations changes the interaction. These interactions depend on the distance between the electron and nuclei as well as the orbital shape. The typical scheme is represented in this diagram 10. Interactions between two dipoles with radius r. The super hyperfine splitting, the further splitting may occur by the unpaired electrons if the electron is subject to the influence of multiple sets of equivalent nuclei. This splitting is on the order of 2Ni plus 1 and is known as super hyperfine splitting. The hyperfine structures split fine structures into smaller components. The superfine structure further split these hyperfine structures. As a result, these interactions are exactly small but are useful as they can be used as direct evidence for covalency. For example, here methanol, an EPR spectrum would show a triple of doublet. The triplet would arise from the 3 protons, but super hyperfine splitting would cause these to split further into doublets. The spin orbit interactions, the energy levels of atomic electrons are affected by the interactions between the electron spin magnetic moment and orbital angular momenta of the electron. It can be visualized as a magnetic field caused by the electron's orbit motion interact with the spin magnetic moment. This effective magnetic field can be expressed in terms of electron orbital angular momentum. The spin orbit interaction is also a magnetic interaction, but with the magnetic field generated by the orbital motions of an electron within the atom itself. Here the L and S are the orbiter and the spin angular momentum of the free ions values, and it is the spin orbit coupling constant of the atom or ion. The effect of spin orbit coupling. When the unpaired electron is placed when a chemical environment or in transition metal complex, the G value does not agree with the expected value. It is explained as follows. The chemical environment or the crystal field strongly perturbs the orbital motions of the electron. Therefore, the orbital degeneracy, if any, is partly removed or quenched. On the other hand, the spin orbit coupling tends to sustain certain amount of orbital degeneracy. The very important point here, crystal field effect. The relative magnitude of crystal field and spin orbit coupling determine the properties of the transition metals to a large extent. These two have opposite effect on the orbital degeneracy. Crystal field tries to remove while the spin orbit coupling prevents the removal of orbital degeneracy. 3 cases can be distinguished here: spin orbit coupling, is very much greater than the crystal field. Effect of crystal field is strong enough to break the coupling between L and S. Effect of crystal field is very large so that LS coupling is broken down completely. To summarize that unit 3, the EPR, also recognized as electron spin resonance and electron magnetic resonance, is a branch of spectroscopy which involves the process of resonant absorptions microwave radiation by paramagnetic ions or molecules containing one or more unpaired electrons in the presence of a static magnetic field. It is discovered by Jaworski in 1945 and become a powerful technique applicable to systems with a net electron spin angular momentum. The EPR has developed into the potent, multi-purpose, non-destructive and non-intrusive analytical method. EPR can provide valuable information on structural and dynamical aspects, even from current, chemical or physical process without influencing the process itself. Therefore, EPR is considered as an ideal complementary techniques for other methods in a wide range of studies in the areas of chemistry, biology, medicine and physics. EPR spectroscopy provides an experimental route to study the magnetic interactions in paramagnetic materials. High sensitivity and high ability to investigate low concentrations of paramagnetic materials, high sensitivity and the ability to investigate low concentrations of paramagnetic ions in powders, polymers and frozen solutions are key advantages of EPR spectroscopy. Additional techniques employing both EPR and NMR method are available and tend to scope of such investigation. EPR spectroscopy can be combined with chemical techniques such as spin trapping to detect and follow free radical relations in biological systems. These are all important questions. Microwaves necessary to study EPR. G factor, what does it mean if the value of 2? Explain the basic principle of ESR spectroscopy, write a note on spin relaxation mechanism, spin lattice and spin-spin relaxation, significance of hyperfine interactions, isotropic and anisotropic interaction, super hyperfine splitting, spin orbit interaction. Define the effect of spin orbital coupling or crystal field effect. Describe the width and position of spectral line in ESR spectrum. Thank you. Thank you, one and all.